Math 3 students, Mrs. Robinson here to work practice benchmark chapter 6 with you. This is a little bit of review from what we did way back in Math 1. Of course, these problems are going to get much more complicated. We're going to do fourth roots and all kinds of radical and rational, meaning they're fractional exponents. So let's get started. Please ignore the big hole in my ceiling over there. I see it in the video, and we had a little flood from the upstairs bathroom, so yay. All right, let's go ahead and get started with this first one. We're going to go fourth root of 81, x to the 20th, y to the 8th. I like to work some of these by breaking them apart into its pieces, which is a valid process as long as everything is the fourth root, and I can multiply it back together, I can break it apart. And the reason I'm going to do this here is because it allows me to see each term I have to do the fourth root to. And it just helps me to see it. You don't have to break it apart like that if you don't find this useful, but this allows me to go, all right, I need 81 to be to the fourth power. Well, let's break down 81. Is 81 something to the fourth power? If you're not sure, get out your calculator and just start with numbers. Go 3 times 3 times 3 times 3, 4 times. See what it gives you. It actually gives you 81. This is 3 to the fourth power. So I'm going to write it like this. So this would be the fourth root of 3 to the fourth. Now these are going to cancel out, and I'm going to get 3. Let's come over here and do this one. Now for me, the easiest thing to do when I'm doing exponents is if this divides evenly, I'm going to set it up into its rational exponent. I'm going to set this up. Remember, the power goes on high, the root goes below. That's how I remember which goes on top or bottom. The power goes on high, the root goes below. Root's in the bottom, power's on the top. And if these simplify by dividing evenly, beautiful. This is just x to the fifth power. And then look, these are going to divide evenly, so I'm going to go ahead and write them in their rational forms because it works. Power is on high, root goes below. And then if I divide this, this is y squared. Now these are all multiplied, and I'm going to talk about the absolute value. This does have to have the absolute value on it. I'm going to talk about that in a second, and I'm going to write my final answer up here because these are all multiplied. This is going to be 3. This is going to be the absolute value here, and I'm going to talk about y just to remind you, the absolute value of x to the fifth, and then this will be y squared. And that will be my final answer. Remember, when you're writing roots and powers, the power goes up and the root goes on the bottom when you're doing rational exponents. You could also write it like this if ever this is helpful. The power could go outside the root. Okay, either of these are acceptable ways to write. Now let's talk about this real quick. Why did I put absolute values around this one and not this one? The reason is just the basics. I'm going to write them over here. All right, guys, this is how I remember when to put an absolute value. If you have an even power and an even root, or you could write even root first, an even root and an even power, and you get out an odd power solution, okay, that is when you need the absolute value. So you have an even root, an even power, and your solution has an odd power. That means absolute value. And the reason is when you put a number in here and you take it to an even power, that number could originally have been a negative number. When you take a negative number and square it, it becomes positive. And then when you square root it or fourth root it or whatever root it, and you come up with an odd power, this x, if that x originally was a negative, let's say a -1, I'm going to say x to the fifth, which is going to mean this is going to be negative. But I cannot have this be negative because when I square root something, I get the principal root, the only positive root. So anytime your original number could be negative, when you take it to an even power and an even root, and you come up with an odd power, that allows that x to be its negative, which it cannot be, okay? Now I don't have to do this. I had an even and an even here. Why isn't this in absolute values? Well, let's look. If x were -1 and I took it to the 8th power, it would be positive. And I took the fourth root, it would be positive. So my solution needs to be the positive principal root. However, it will be because I'm squaring it. So that's why if it is an even powered solution, I don't have to worry about these absolute values. Only if it's an odd powered solution. That's the only time I have to worry about those absolute values. So think even root, even power, odd power solution, throw those absolute values on there. Okay guys, let's look at number 2. I'm going to go ahead and break this apart because I think it helps me. You don't have to. I'm going to go, I want the cube root of 27, and then I'm going to multiply that by the cube root of, sorry, that's a cube, of x to the 15th. And then I'm going to multiply that by the cube root of y to the 24th. Okay, let's start here. I know 3 cubed is 27, so this is 3 cubed and the cube root of it. The cube and the cube root cancel and I get 3. Now this is easiest to do if these divide evenly, and they do. So I'm going to take it to my rational power, and I'm going to go 15 divided by 3, which gives me x to the 5th. And that's a multiply. Now let's look. Did I have even roots and an even power to an odd power? I do have an odd power solution, but I had odd powers here, so this is allowed to be negative. All right. Now I have an even power but an odd root, so once again I'm fine here. I don't have to worry about it. It's just the even to the odd powered solution. So let's go ahead and do this one. I'm going to see, does 24 divide by 3? Let's do power and root. Power's up, root's down. It does. This is going to give me y. 3 goes into 24 8 times. And there's my solution. 3x to the 5th, y to the 8th. I don't have to do any absolute values on this one. All right, let's see if breaking this one apart helps me at all. I've got the cube root of 108. And I want to multiply that by the cube root of a to the, that is an ugly a, to the 16th. And then the cube root of b to the 9th. All right, let's look at these. The cube root of 108. I don't think 108 is a perfect cube. So I'm going to break this apart. What divides nicely into 108? I played with this a bit. You can play with it on a calculator, but 108 is actually 27 times 4. Now I could break this into its primes and see what's cubed, but I know 27 is a perfect cube. It's 3 cubed. So what I have here is the cube root of 27 times 4. I'm going to break this into the cube root of 27 times the cube root of 4. 4 is not a perfect cube, 27 is. This breaks down into the cube root of 27 is 3. That does not break down. I have to leave it as the cube root of 4. And then I'm going to multiply it by this. Well, 16 is not divisible by 3. When that happens, I have to break this apart. I'm going to break this into something that is divisible by 3. I know that a to the 15th is divisible by 3, and then I have 1 left over times a. So this is the cube root of a to the 15 times a. I'm going to break this into the cube root of a to the 15 times the cube root of a. So break those apart, and that was supposed to be a 3. All right, and then I'm going to put this into its rational exponents, a to the 15 over 3, and I'm just going to leave this because that doesn't help me to put it in its rational exponent, is the cube root of a. When I divide this out, it gives me a to the 5th power. So this is all multiplied. So what I have now here is 3 cube root 3 times the cube root of 4 times a to the 5th times the cube root of a. Now come over and do this one. This does work nicely. 9 is divisible by 3, so I'm going to use the power and the root, make a rational exponent. B to the 9/3 reduces to b to the 3rd power. And then I'm going to bring that down. This is all multiplied together. This is b to the 3rd. Now I can simplify this. Anything that was, this is all multiplied together, so order doesn't matter. So I'm going to reorder this nicely. These are both under the cube root, so I'm going to multiply them back together and put them under 1 cube root. So I'm going to have 3 times a to the 5th, so 3a to the 5th times b cubed times the cube root of 4a. And there is your solution. And let's just double check and make sure we didn't have any even, odd scenarios. We have an even, odd, that's fine. We have an odd, that's fine. So we don't have any absolute values. All right, let's look at number 4. We've got 2 square roots. The square roots are a little easier to work with. I can put these together if it helps me. Now here's how I find it helps me. If anytime you have like terms, you do want to put them together to see what it turns out to be. So we've got 2 numbers, so let's rewrite this. This is going to be the square root of 50 times 6. And then we have an x to the 7th. Since they're both square roots, I can multiply them together. X to the 7th times x. Same base, you add exponents. That will be x to the 8th. And then y to the 7th times y to the 4th. Same base, add exponents. Y to the... All right. So here we have our whole term under the root. Now let's go ahead and break out square roots. Well, 50 is not a perfect square, but I know that 50 is 25 times 2, which is a perfect square right here, 25. Now the 2 is left over, but 6 is not a perfect square. I know that's 3 times 2. Now I've got 2 2's that I can make a perfect square and a 3 left over. So let's rewrite this as 5 squared for 25 times 2 squared times 3. There is our constant. Let's look at our variables. I have x to the 8th, then I have y to the 11th. So let's go ahead and break this into the square root of this times the square root of this times the square root of this. And we'll deal with each one individually. Now this, I can pull out a 5 out of here and square root it. Square root of 2 squared, the 2 pulls out. And the 3 stays in the root. So what I have is 2 times 5 on the outside, or 10. And then I have the square root of 3 inside. Now there are various ways to do this. I could have multiplied 50 times 6 and then broken it apart like that, and I would have 100 times 3. That would have worked. You would have seen it's 300, and then you just pull out the square root of 100, which is 10. So there's multiple ways to do this. All right, now because I have an even power and a square root, I'm going to make the rational root. I'm going to go x to the 8 divided by 2, and then that's going to give me x to the 4th. And then this is odd. It doesn't divide nicely, so I'm going to break this apart to the square root of y to the 10th times the square root of y. Multiplying that together, that gives me y to the 11th. This will work nicely. I can write this as y to the 10 over 2, or just y to the 5th. And that doesn't go anywhere. It stays under the root, square root of y. So let's write this is multiplied by this, which is multiplied by this, multiplied by this. I have to write them all together. This is going to be 10 root 3 times x to the 4th times y to the 5th times root y. Now let's just double check. We had an even and an even. Did we have an odd solution though? No. We had an even to an even. That to the 4th power will make sure this stays even. So we're okay. We had an odd power and an even root. Odd to even is fine. It's the even, odd that's the problem. Because when you square those odds, they have to stay positive. All right, now we're finished with this. Let's just reorder it and make it look nice. This is under a root and this is under a root. Let's put it all under one root. So we're going to go 10 x to the 4th, y to the 5th, times the square root of 3y. And you're finished. This one has a division right here. Now we know there's something called rationalizing the denominator, meaning we don't like square roots in the denominator. Now sometimes it's okay to leave it like that if you're dealing with a real world situation and you're actually going to use a square root button on a calculator where you're going to find some kind of rounded number. But in this point, when we want it to be exactly accurate, we rationalize our denominator. But before we do that, let's simplify this as much as we can. Just like multiplying 2 roots together is under one root, dividing 2 roots is under one root. So we can rewrite this whole thing like this. The square root of 6 x to the 8th, y to the 9th, over 5 x squared, y to the 4th. Okay, now 6 and 5 aren't divisible, but x to the 8 and x squared is reducible. Okay, so same base, subtract exponents. This is going to be x to the 8 minus 2, which is x to the 6. Same base, subtract exponents. 9 minus 4, and we're going to get y to the 5th. And then 6 divided by 5, that doesn't change. It's just 6 over 5. That's still under the root. And this is what we have simplified. Now we can rewrite this back like this, the root of 6x to the 6th, y to the 5th, divided by square root of 5. If you leave it like this, you're not most simplified if you have any kind of fraction in your root. So undo your fraction, and when you do that, you realize you still have a root on the bottom. You got to rationalize that. And how you do that is, if it's a square root, multiply it by itself, because you basically are squaring it. You have to do it to the top and bottom. That's like multiplying by 1. When I do this, I end up with the square root of root 5 times root 6 will be root 30, x to the 6th, y to the 5th, over root 5 times root 5 is just 5. And that would be your final solution. Don't leave it like this. Leave it like this. All right, we're on to adding, and then we're going to do some multiplying of radicals. The nice thing about adding radicals, you treat them just like a variable. I know it's root 2x, but you treat it like it's a variable. It has to be, or sorry, it's 4th root of 2x. It has to be exactly identical in order to add them. So you have 2 4th roots of 2x and 6 4th roots of 2x. Those are exactly identical, so that would be a total of 8 4th roots of 2x. There's 8 of them, all right? Treat them just like a variable. Now here we have 4 cube roots of 3x plus 5 cube roots of 10x. Well, this is the cube root of 10x, and this is the cube root of 3x. These are not the same. You cannot add them. If you could simplify this somehow and pull this out of here so that this is the exact identical root to this, then you can add them. But 10 breaks down into 5 times 2, and there are no perfect cubes to even pull out to make this work, to make it look like this. So this is not addable. This is done. So this is completely simplified. So done. No more simplifying can be had. All right. Let's go ahead and look at this one. This is a multiplication problem, and this is just FOIL. Treat the roots like variables. So FOIL it out. First term, so 7 times 8 is 56. Then you're going to go outer, plus 7 times root 2 is 7 root 2. Then inner, negative root 2 times 8 is negative 8 root 2. And then last, root 2, negative root 2 times positive root 2 will be negative root 2, and then you're going to square that. Now the beauty of that, doing that, when you square the root, well, the root and the square root cancel, so you just have negative 2 here. So what I have is 56. These are identical roots, so I can add them. 7 root 2 minus 8 root 2 will be negative 1 root 2, or just negative root 2. 56 minus root 2 minus 2. Well, the 56 and the 2 can combine, and I'm going to write this over here. I'm going to get 54 minus root 2. And now I'm completely simplified. All right, on to the next one. Oh, sorry, bud. Thanks. If I have negative 5 minus root 3 squared, this is the same thing. I'm going to go negative 5 minus root 3, and you can write it out if you want, times negative 5 minus root 3. You're squaring the whole thing. Sorry, that was supposed to be a 3. Be very careful. The most common mistake I see is people trying to square this like this. That would be if these two were multiplied together, you could square them, but they're not. This needs to be FOILed out, okay? It's this times itself. FOIL it. Negative 5 times negative 5 is positive 25. Negative 5 times negative root 3 will be positive 5 root 3. Negative root 3 times negative 5, it will be positive 5 root 3 again. So there's always 2 of the middle term when you square it. And then negative root 3 times negative root 3 will be positive root 3 squared. And this will make the square and the square root cancels, just makes 3. So we have 25 plus 3 and 5 root 3 and 5 root 3. There's 5 here root 3's and there's 5 more root 3's. That makes 10 root 3's. They are identical terms. You can combine them. And then one more combining, 25 and 3, that's a plus. 25 and 3 will be 28. I lost my 28. 28. 25 and 3 is 28. Plus 10 root 3. And you're done. All right, on to the next one. Now this one is what it would look like if you multiply by conjugates to try to get rid of the roots. You have like the difference of two perfect squares. So you have 5 times 5, and that gives you 25. And then 5 times plus root 2 is plus 5 root 2. Negative root 2 times 5 will be negative 5 root 2. And that's the beauty of the positive and the negative. These terms will cancel out. And then negative root 2 times negative root 2 will be negative root 2 squared. And just this part is squared, not the negative. So we've got 25, and then 5 root 2 minus 5 root 2, that's 0. And then negative the root 2 squared, the square and the square root cancel, and you just get minus 2. 25 minus 2 is 23, and you're finished. Let's look at this one. This is a little bit tricky one. Normally when we rationalize the denominator, we multiply square root top and bottom. And the reason we do that is when something's squared, and I multiply it by itself, for example, the square root of 2, if I multiply it by itself, actually let's make this be the square root of 6, just to show you if that was a square root, not a cube root. And I multiply it by itself, well, that's essentially squaring it. This will be 6 square root of 6 squared. And the square and the square root cancel, it gives me 6. That's how I get rid of that root. I have to do to the top and the bottom to make 1, but that's what I do. But when it's a cube root, if I were to multiply the cube root by itself, let's do that. The cube root of 6 times the cube root of 6, well, that gives me the cube root of 6 squared. The square and the cube don't cancel. That's not going to work. So I got to figure out how to make this be 6 cubed. So instead of multiplying it by itself, what I need to do is multiply it by the cube root of 6 squared. Because then when I multiply these out, let's see what happens. I need that to be 6 cubed inside, so the cube and the cube root cancel. When I multiply it by 6, the cube root of 6 squared, I get the cube root of 6 times 6 squared, which is 6 cubed. Now the cube and the cube root cancel. So that cube root is a little trickier when you have to rationalize it. So doing it to the bottom, I have to do it to the top. I was showing you how to do the bottom just to show you, but I have to do it to top and bottom to make it a legal operation. And the reason is you do it to the top and bottom, it's like multiplying by 1. So when I do it to the bottom, the cube root of 6 squared is what I'm going to do here. That gives me the cube root of 6 cubed, and the cube root cancel, and I get 6 on bottom. That eliminates the root, the radical. Now let's do the top. I have to multiply this times 2, so that will be 2 cube root of 6 squared, and then I have to multiply this by this, plus, since these are both cube roots, I can put them under the same root. The cube root of 6 squared times 3, well, 6 squared is 36, and you want to multiply that by 3. Let's break this down. So this could be the final answer if this doesn't simplify anymore, or this. Now, let's look and see if it does simplify. So what we're looking at here is 6 squared is 36. So let's come over here with 36. We have the cube root of it. Is this something cubed? Well, 36 could be 6 times 6, or let's go 9 times 4. 9 is 3 times 3, and 4 is 2 times 2. So what we break down is to 3 squared times 2 squared if we break into the primes, and that would be the cube root, and none of those are cube roots. They're only squares, so I cannot break this down anymore. There's no perfect cubes. What about this right here? 36 times 3, let's look at that cube root over here. Well, 36 times 3 is 108, which we know breaks into 36 times 3. And 36 we just did is 9 times 4, and that actually breaks into 3 times 3, and then 2 times 2. And we have a 3 here. So look, this breaks into the cube root of 3 cubed times 2 squared. This is a perfect cube. the cube and the cube root cancel, and this comes out of the root and becomes 3. And then it leaves you with the cube root of 2 squared, which is 4. So 108 breaks down into 3, the cube root of 4. That's what this breaks down into. So we've got 2, the cube root of 6 squared, which is 36. It's like a little puzzle, right? And then here, you're looking for anything that will be a perfect cube, and we found one, 3 cubed. So break it into its primes if you have to. This is the cube root of 3 on the outside. It's supposed to be a 3 on the outside, times the cube root of 2 squared, which is 4. That's what was left after I pulled out that 3, and I was left with 4. And then that's all over 6 on the bottom. So rationalizing the denominator for this is a bit tricky, because once you figured out how to get the cube and the cube root to cancel, it made this a little tricky for simplifying. All right, good luck on that one. Simplify this. Okay, once again, we want our denominator not to have any roots in it. That's just a little math simplification rule. So in order to do that, we have to rationalize the denominator. And when you have 2 separate roots like this, I can't multiply by root 3 or root 6. What do I multiply to get both of these roots? You multiply by its conjugate. So you're going to multiply by root 3 minus root 6. If you do it to the bottom, you got to do the same thing to the top, root 3 minus root 6. The conjugate is like multiplying by, what would you have is if you had the difference of 2 perfect squares. The middle term falls out. That's the beauty of this. If the middle term doesn't fall out, you'll have a root in the middle term, and you don't want that. So if that's plus, that's minus. Let's go ahead and do our multiplication on the bottom. Root 3 times root 3 is root 3 squared, which is 3. Then root 3 times root 6 will be negative root 18. Root 3 times positive root 6 will be positive root 18. And then root 6 times negative root 6 will be negative root 6 squared. So that's my bottom. Oh, I put a cube there, and I meant to put a 2 there. I apologize. All right, so the square and the square root cancel, and I get 3. The square and the square root cancel here, and I get negative 6. Negative root 18 plus root 18, those go away, and this is how it happens. 3 minus 6 gives me negative 3. So my denominator here is negative 3. All right, now let's do the numerator. It's going to be a little bit more complicated. Root 3 times root 3, I'm going to write it over here, is root 3 squared again. And I wrote the square this time. Root 3 times negative root 6 is negative root 18. And then negative root 6 times positive root 3 will be negative root 18 again. And then negative root 6 times negative root 6 is positive root 6 squared. So that cancels and I get 3. That cancels and I get 6. These don't cancel. I get 2 of them. There's 2 root 18. So negative 2 root 18. And then 3 plus 6 is 9. So this will be 9 minus 2 root 18s. So, and that is an 8, sorry. So on top, I'm going to have 9 minus 2 root 18s. Now, is that the final answer? Well, does root 18, does it have any perfect roots that can come out of this? It actually does. So let's go ahead and simplify over here. I know 18 is actually 9 times 2, and 9 is a perfect square, so that simplifies even more. So let's rewrite. If I have the root 18 over here, I know 18 is actually 9 times 2. So this is the square root of 9 times 2. 9's a perfect square. It is 3 squared. So this is 3 squared times 2. This comes out of the square root and becomes 3. So I have 3, and then the 2 is not a perfect square, it stays inside. So I have 3 root 2. That's what I have for the root 18. 18 is equal to, or excuse me, root 18 is equal to 3 root 2. So I simplify this to 3 root 2, and I still have to multiply it by negative 2. So what I have here is 9 minus 2 times 3 root 2 over negative 3. Now let's simplify this. 9 minus 2 times 3 is 6 root 2 over negative 3. Now you think you would be done there, but oh look, The negative 3 divides into 9 and 6. So you can do a little bit more simplifying, distribute from the bottom to, since it divides into both numbers, you can simplify. 3 divides into 9, 3 divides into 6. So negative 3 into 9 gives you negative 3. Negative 3 into negative 6 gives you positive 2 root 2. And that's your final answer. A little complicated. Okay, so this is how you're gonna, hold on. What, bud? We gotta write this using positive rational exponents. So we're gonna write this using all positive exponents, and they're gonna be rational, meaning like the fractional exponents. Let's do that. First thing we want to do is we're going to turn this into a simplified form. Well, the cube root of x cubed is just x. So that's just x. Easy. Now, the fifth root of x squared, let's make that be a rational exponent. That's going to be x. The power goes on high, the root goes on bottom. That's how I remember. That's the power, that's the root. Power goes high, root goes in the ground. Now, to simplify this, we know a rule. If you have the same base, they're both x's, you can subtract their exponents. Well, this is the same as x to the first. So I'm going to write this as x to the first minus 2/5. Same base, they have the same base, you subtract their exponents. That would be like if I have x to the fourth divided by x, well, that's just going to be x to the 4 minus 1, which is just x cubed. And you can check that, write it out. This is 4 x's on top, 1 x on bottom, 1 x divides out and leaves you with 3 x's. So the rule works, just double check it. All right, so if I subtract exponents here, I'm going to go 1 minus 2/5. Well, I got to make that a fraction. And the denominator I want it to be is 5, and that's easy. I'm just going to make this x to the 5/5. 1 is the same as 5/5 minus 2/5, and that's just going to be 3/5. So this is x to the 3/5 power, and there I have it, positive rational exponents. It's the same as the fifth root of x cubed. All right, let's write this in simplest form. Simplest form means all positive rational exponents, okay? All positive or roots. Nothing on the denominator, no negatives on the denominator. All right, so looking at this, this guy, because these are multiplied together, I can distribute him to both terms. So I'm going to write this as 8, and I'm going to take 8 to the negative 2/3 power. And this is also going to be a to the negative 3, and I'm going to take that to the negative 2/3 power. Okay, this distributes. This would be the same if I had like x, y squared, and I was cubing it. I would cube the x and I would cube the y squared. This would be x cubed, y squared cubed. And then a power to a power is a multiply problem. This would be x cubed, y to the 6th. And you could check that rule by writing x, y squared 3 times, and this is what you would get. All right, so double check your rules. Now, before I go any further with this 8, I'm going to break down into its primes and see if I can make this a little simpler. I know 8 is 4 times 2 and then 2 times 2, and you probably already know 8 is 2 cubed. So write 8 as 2 cubed. This is 2 cubed to the negative 2/3 power. Okay, a power to a power is a multiply problem. So this is 3 times negative 2/3. Well, the denominator cancels with the numerator and just leaves me with negative 2. So when I multiply this across, I'm just going to get, and let's write it down here, I'm going to get 2 to the negative 2 power. The 3 and the 3 cancel when I multiply and I get negative 2. Now this, a power to a power is a multiply problem, so this is negative 3 times negative 2/3. And you can put this over 1 if you want, but the 3 and the 3 cancel, and that leaves me with negative 1 and 1 on bottom, if you want to think of it like that. Negative 1 times negative 2 is just positive 2 over 1, which is just 2. So when I multiply this, the 3 and the 3 cancel, and the negative times the negative makes a positive 2, and I end up with a squared. So what I have here is, let's write it down here, 2 to the negative 2 times a squared. Well, what does that look like? That looks like a squared. And then if I don't want negative exponents, when I have a negative exponent, I bring it to the bottom and make it a positive exponent. So this will be 2 to the positive 2. So a squared times 2 to the positive 2. Bring that to the denominator to make it a positive exponent. And then that's just a squared. Well, 2 squared is just 4. So there's your final answer, a squared over 4. On to number 15. Okay, when you're solving radical equations, you often square both sides. Okay, we're going to solve some radical equations. Just remember, when you solve radical equations, you're going to have to square both sides to get rid of that square root. You often create extraneous solutions, and I think of it like this. If you have negative 2 and you square it, you get positive 4. If you have 2 and you square it, you get positive 4. So sometimes when you square both sides, you create an extraneous solution that doesn't exist. You could have had a negative or you could have had a positive. Let's just be careful to check solutions. That is the most important thing when solving radical equations. Check solutions. Second thing you want to do, when you solve radical equations, isolate the radical first, then square both sides. So we're going to get rid of the 7. Add 7 to both sides. That's going to give us radical x plus 10 equals negative 5 plus 7 is 2. Now I'm going to square both sides to get rid of that radical. The square and the square root cancel, and I'm going to bring this up here for space. I'm going to get x plus 10 equals 2 squared is 4. Now solve for x, subtract 10 from both sides. That's a 10. And you're going to get x equals 4 minus 10 is negative 6. Okay, this looks like a solution. Check it. You may come up with solutions that don't actually work, and you're going to tell me it's a solution. You're going to get marked wrong because you didn't check it. Plug this in here and see if this is valid. Negative 6 plus 10 gives you positive 4. The square root of positive 4 is 2. 2 minus 7 is negative 5. Check. That one works. You're good. Let's go on to 16. Okay, when we're solving problems like this, once again, isolate the root. It is a 5th root. Isolate it first before you do anything else. So let's get rid of the 3 on both sides. And you're going to get 2 radical 5th root of x plus 6, that whole quantity cubed, equals 16, or 19 minus 3 is 16. Now I want to get rid of that 2 before I isolate this, to isolate this radical. So divide by 2. Now I've got the 5th root of x plus 6 cubed equals 16 divided by 2, which is 8. Now, a couple ways you could do it. The book tells you to turn that into a rational exponent and then do the reciprocal of both sides. When you do that, you need to be careful, because if the top or the bottom is even, you have to show the absolute value, meaning it could have been positive or negative solutions, okay? Or you can just undo it. So I'm going to show you both ways. If I want to undo this, I'm going to take it to the 5th power. So I'm going to go 8 to the 5th power, okay? That eliminates the radical, and then I'll bring this up here. What I have left is x plus 6 cubed equals 8 to the 5th. Now to get rid of that, I still have to solve for x, so I have to cube root both sides. Cube root both sides. That gets rid of that power, and then I get x plus 6 equals the cube root of 8 to the 5th. Now when I cube root, I don't have to show a plus or minus solution because it's a cube root. If it's negative, it's negative. If it's positive, it's positive because it's an odd root. If it was an even root, I would have to show the plus or minus solution. Careful with that. Okay, so I'm going to cube root, and I get the cube root of 8 to the 5th. And then to solve for x, I subtract 6 from both sides, and I'm going to get x equals the cube root of 8 to the 5th power minus 6. Does this simplify? Well, this is the same as 8. This is a power of 5 divided by 3 minus 6. Okay, that's what x equals. Now, 5 doesn't divide by 3, so that doesn't help me. So I'm going to break this up. And I'm going to say, well, let's see. I know 8 is 2 cubed. And I'm going to take that to the 5th power. And then I'm going to cube root that. Now remember, the square root, or excuse me, the cube root of x to the 5th is the same thing as the cube root of x to the 5th. I can take it to the 5th power and then root it with the cube root, or I can cube root it and then take it to the 5th power afterwards. It doesn't matter what order I do it in. So I'm going to write this as the cube root of 2 cubed, which is 8, and then take it to the 5th power. That's way easier because taking 8 to the 5th power, that's a huge number. I don't know what that is. So by doing that, the cube and the cube root cancel, and I get 2 to the 5th power. 2 to the 5th power is way more doable. And then minus 6. I'm bringing this down here. So x equals 2 to the 5th minus 6. Well, what's 2 to the 5th? Do that on the calculator. 2 to the 5th is 32. So I got 32 minus 6. And I'm going to get 26. So x is going to equal 26. Now check it, plug it in, make sure it works. 26 plus 6, cube it, 5th root it, multiply it by 2, add 3. Does that equal 19? It does. Okay, the other way the book shows how to do it real quick, let me erase this part. Okay, the book, just from this point, if you had the 5th root of x plus 6 cubed, and then we simplified that to equal 8. So if I took this and wrote it as its rational exponent, this would be x plus 6, and this is its power and that's its root. So the 3/5 power equals 8. Now the book tells you, solve this, just multiply by its reciprocal, 5/3. You just have to be careful if the top or bottom is even, you have to make sure your solution has absolute values, okay? And what I mean by that, if neither of these are even, it's odd, but let's take both to the 5/3 power. So these actually cancel and give you to the 1st power. So this would be x plus 6 equals 8 to the 5/3, which brings us back to that same point we were before. If either of those were the root or the power were even, it would have to look like this. The absolute value equals this. And then you would have to do 2 solutions. X plus 6 equals positive this, x plus 6 equals negative this. Just be careful if you use that method. All right, because when you square root, you show a plus or minus solution. All right, or 4th root or any even root. So let's go ahead and we already simplified this. This is the same thing as 2 cubed. It's the cube root to the 5th power. And then we cancel these and we got 2 to the 5th power. And so we once again end up with the same solution. X plus 6 equals 2 to the 5th is 32. And then you subtract 6. You can subtract 6 at the end or the beginning and you get 26. So you're going to end up with the same solution either way. All right, to solve this, once again, isolate the radical. So let's first get rid of the 8 on this side. And we're going to end up with the square root of 3x plus 28 equals x plus 8. Now we've isolated the radical. Now we get to square both sides. So the square and the square root cancel, and we're going to end up with 3x plus 28 equals x plus 8 squared. Now that's annoying. I can't just distribute that because that's a plus. These aren't multiplied. I have to go x plus 8 and multiply it by itself. If you know how to FOIL that out, if you know it's 2 times this in the middle, you can do that, or just FOIL it. This times this is x squared. This times this is 8 x's, outer, 8 x's, last, 8 times 8 is 64. Okay, and this is x squared, and then these give you plus 16 x's plus 64. So I FOILed this out and it gives me this. Okay, that's what that is after I FOIL it out. So let's come up here and write it like this. Let's simplify. We're going to go 3x plus 28 equals this whole blob I just FOILed out. X squared plus 16x plus 64, yay. Okay, now let's go ahead and solve. We're going to subtract 3x from both sides. And the reason we do that is because we want to get everything on one side because we have an x squared and an x. We're going to get everything on one side and then we're going to have to factor. Hopefully factoring works and we don't have to use quadratic formula. So we subtract 28 from both sides also. bring down, and we're going to get 0 equals x squared. Subtracting 16x's, or excuse me, subtracting 3x's from 16x's, you're going to get 13x's. And then what's 64 minus 28? What is that? 36? You set it equal to 0. Then let's factor this using zero product property. We'll figure out what will make this work. So x goes here and here. We need to figure out the factors of 36 that make 13, and sometimes I do it like this. What factors of 36 will make 13? So we need 13 here and 36 here. Well, 9 times 4 makes 36, and 9 plus 4 makes 13. There they are, 9 and 4. All right, let's check the positives and negatives on that. This is positive, that's positive, so we got to have positive, positive. All right, this times this makes 0, so for this to be 0, x has to be -9. For this to be 0, x would have to be -4. So my solutions are x is -9 and -4. Now careful, if you give me both these solutions, one of them could have been extraneous. We squared both sides. Check and see if they both work. Plug in -9. -9 times 3, that is -27. -27 plus 28 is +1. So this becomes +1, and the square root of +1 is 1. So this becomes 1. 1 minus 8 equals, and then what was x? X was -9. Does that equal -9? Does 1 minus 8 equal -9? No, it equals -7. This doesn't work. We made an extraneous solution. If you tell me the solution is -4 and -9, you're going to get it wrong. Check -4. Make sure that one does work. 3 times -4 is -12. Let's go. What's 28 minus 12 is 16. Square root 16, you get 4. 4 minus 8 is -4. -4 was my x I put in on this side. Does 4 minus 8 equal -4? It does. This is a solution. So if you didn't check your solutions, you would have gotten this wrong. Careful, you would have done all that work and then come to here and not had the right solution because you had an extraneous solution. So careful with the online test with those extraneous solutions because we'll give you both those choices. So very, very, very careful. All right, let's go on to composite functions. We're just adding functions. These are super easy. Once again, review from Math 1, just a little more complicated. You're adding the f function and the g function. You literally just take the f function and you add it to the g function. So I just go -5x minus 4 plus the g function, 6x minus 7. Combine like terms, -5x's plus 6x's is 1x. -4 minus 7 is -11. So f of x plus g of x, and that doesn't look like an x, that looks like a y, equals x minus 11. That's all you have to do. Let's do some subtraction on the next one. We're just taking the f function and subtracting off the g function. So I'm going to go 4x minus 5, and I'm going to subtract. Careful, I'm subtracting the whole thing. This is where the mistakes happen. You guys just subtract the 6 and you forget to distribute the -3. I said you guys, but some people forget. Not everyone. Okay, so let's go ahead and distribute. So we'll have 4x minus 5, distribute, -6x, and then plus 3. Combine like terms, 4x's minus 6x's are -2x's. -5 plus 3 is -2. So f of x minus g of x is this function, our new function, -2x minus 2. All right, let's do the next one. Find f times g. So let's do f times g. That's our next guy. We're going to test you on all of these. Literally, to do f times g, you just multiply the functions. Multiply this times this. So we're going to go 3x plus 2, and we're going to multiply it by 7x plus 6, and it's a FOIL problem. First terms, this is going to give me 21x squared. Outer terms, this will give me 3x times 6 will give me plus 18x. inner terms, 7 times 2 x's will give me 14 x's. And then last terms, 2 times 6 will give me plus 12. Simplify, you're going to go 21x squared. Combine the like terms in the middle. Let's see, 18, 28, 32, plus 32 x's plus 12. So this is f times g of x. There it is. And then let's go f divided by g of x. And then this does say state its domain. Its domain here, all the real numbers work. I can plug in anything here. There's no divisions or any restrictions or roots or anything that might be weird. I can plug in everything I want here. My final solution, I can plug in anything I want here too. If it's negative, it's positive. So my domain is going to be all real numbers. And I write it like the big R. You can write all real numbers if you want. All right, we need to state the domain for 21. So let's do that. We're doing f divided by g of x. So we take our f function, x squared minus 16, and we divide our g function, x plus 4. Okay, let's first state domain with our original function, because this is f over g unsimplified. This is what it looks like. We're going to simplify it, but let's state our domain before we simplify it. And the reason is, look at the denominator. Anytime you divide by a variable, you have restrictions. I can plug in anything I want for x, really, anywhere. So it is going to be all the real numbers, except for I cannot divide by 0. What on the denominator makes me divide by 0? If x is negative 4. Negative 4 plus 4 makes 0 on the bottom. So x just cannot be all real numbers, except x cannot equal negative 4. Okay, that's my domain. All real numbers, but not negative 4. So let's go ahead and simplify this. I can factor this as the difference of perfect squares. This is x minus 4 times x plus 4. Remember your factoring, okay? That's a perfect square, that's a perfect square, that's a minus sign. If I multiply this back out, the middle terms fall out, and I get this. And then here's my denominator, x plus 4. And then these cancel, and I'm going to get x minus 4. When you guys start graphing rational functions, you'll realize this starts out, it's a removable, okay? So instead of being an asymptote at negative 4, you have a hole in the graph because it divides out, it becomes a removable, all right? So x minus 4 is f of x divided by g of x, and that is my domain. Now let's do the hardest part, the composites. G of f of x, and actually g of f of negative 5. So I always say they're like the dolls that fit one into, like the Russian dolls. There's the little one and then the bigger one and the bigger one. And I like to rewrite this just for understanding. F of g of negative 5, it looks like this. Or excuse me, g of f of negative 5. I said that backwards. So g of f of negative 5. So you know what to do first. You start inner. Okay, so in this order, you start inner, you put negative 5 into the f function, and then you put that answer into the g function. So we start with negative 5, and we're going to put negative 5 into the f function. So let's do that. Plug negative 5 into the f function. So that means find your f function, here it is. Wherever there's an x, you plug in a negative 5. So f of negative 5 looks like this, negative 5 plus 2. So your f of negative 5 is just negative 3. Now we found that, we plug it in here. So now we get to plug in negative 3 for f of negative 5. So now we take that answer, we plug it into the g function. So now we have g of f of negative 5. We figured out this, so we want g of, we plug this in for f of negative 5, that's negative 3. So we plug this into the g function. Here's my g function. So g of negative 3 means I plug in negative 3 for x here. Negative 3 squared, and that's going to give me g of f of negative 5, or g of 3, which gives me 9. All right, this gives me 9. So this is this, we're just plugging in negative 5 into the f function. We get that answer, we plug it into the g function. So plug this into here, and then plug this into here. That's how you have to think of it. All right, so g of f of negative 5 is 9. On to the next. What's the inverse of this? Inverse is whether you have a big mess of something or whatever it might be, you just do the simple form of replace the x and y, or excuse me, exchange the x and y and solve for y. If this says f of x instead of y, just make it be y for a minute. All right, so your job is to change the x and y out. So we're going to go x equals 7y squared minus 3. So change x and y, then solve for y. And that's how we find our inverse. So I changed them, now solve for y. So just put it back in its form. So this technically is the inverse because I changed the x and y. If I was just having a table, I would literally just switch these values to find the inverse. Okay, but let's solve for y so we actually have our function in the form we want. We're going to add 3 to both sides. And we get 7y squared equals x plus 3. Let's put this up here, and I'm just going to flip them around just because I like the y on this side. 7y squared equals x plus 3. Still solving for y, so get rid of the 7. Divide this whole thing by 7. You're going to get y squared equals x plus 3 over 7. Now square rooting, whenever you root, we talked about this, you get 2 solutions. You have a positive and a negative solution. Make sure you show both solutions. Okay, the square and the square root cancel, and y is going to be a positive solution and a negative solution. The square root of x plus 3 over 7. That's why when you solve those absolute value equations and you square both sides and then you undo it, you have to do the absolute value so that you show both positive and negative solutions. Okay. You don't know if x, when you squared it, you square root it, you don't know if that was a positive or a negative. So there is your inverse, all right? And that is what it looks like. That is what your function looks like. Here's your function, here's your inverse function. All right, onto the graph. Okay, we want to graph this and its inverse on the same axis. So first let's find its inverse. And remember, inverse functions, no matter what they look like, if you can somehow graph the function, the inverse function is always a reflection across the line y equals to x, this line right here. So whatever the graph looks like, flip it across that line, and then you'll have your inverse. Sometimes it's hard to see though. All right, so let's look at this. We just have a line. So if I want, here's my line, let's find its inverse first. The inverse is going to be change the x and y. So I'm going to go x equals negative 2y plus 3. There, I changed my x and y. This is my inverse, but let's solve for y. So let's do that. Let's just first move the y to this side to get it on this side of the equation. So we're going to have 2y plus x equals 3. Now move to the x to this side. So you're going to get 2y equals negative x plus 3. Then divide by 2 on both sides. You're going to get y equals to negative x divided by 2 and 3 divided by 2. So let's make this negative 1/2 x plus 3/2, which is 1.5. So there is my inverse line. Here is my original. This is just my regular function. Was this one, y equals to negative 2x plus 3. Okay, now you can graph this by plotting points. You could have plot points. You could have gone x, y. Let's plug in some points and then flip those points and graph your inverse. That would have been an easy way to go. But since these are both lines, this is easy, guys. Let's just go slope. M is your slope, so your slope is negative 2. B is your y-intercept. Your y-intercept is 3. This guy's slope, your slope is next to the x. If you don't remember, I'm just going to write this up here. Y equals mx plus b, the equation of a line we use forever. The number next to the x is the slope, and the constant is your y-intercept. So your slope here is negative 1/2. Your y-intercept is 3/2. We can write that as 1.5 if you want. All right, so let's go ahead and graph this guy's y-intercept is 3. So I'm going to go here to 3, do the y-intercept, and then its slope is negative 2. Or negative 2 over 1. Remember, rise over run. And since it's negative, I fall first. So fall 2 over 1. Fall 2 over 1. fall 2 over 1. You can do as many as you want. Fall 2 over 1. Or you could do it, flip it. Rise 2, back 1. You could go rise 2, back 1. All right, so let's go ahead and draw a line through there. And no, that is not a good line. Let's try that again. Let's do this guy through here. All right, there's a line. And then let's go ahead and graph the other one. We want our, let's see, our slope and our y-intercept. So our y-intercept is 1.5, so we're going to go up 1.5. My slope is also negative, but it's negative 1 over 2. So I'm going to fall 1 over 2. There's my point. Fall 1, and I'm going halfway, because I'm halfway here, over 2. Fall 1 over 2. Fall 1 over 2. And that is what that line should look like. And let's see if we can pull this through as nice as I can. All right, so there's that line. And then just check it. Make sure it is symmetric about the line y equals to x. And it is. So it is symmetric. It folds in half over that. Okay, so inverse and the function. Graph the function. The inverse, switch x and y, solve for y. Now, if you just want to plot some points for the function and then flip the points, wherever there was a y, make it be an x, you can graph it that way too. Let's do the last one. Okay, this last one I'm going to show you how to graph by shifting the original function. You could also graph this by plotting some points, all right? So that's up to you. If you just want to go like this, here's some xy points. I'm going to plug in some points and figure this out. Start with, 2 and makes this 0. You can do that. I'm going to show you how to graph this by graphing the parent function and working all the shifting, okay? So looking at this, the parent function y equals to the square root of x. Okay, it's basic points. If you look on the graph, okay, there are no negatives. We can start with 0. The square root of 0 is just 0. Plug in 1. The square root of 1 gives me out 1. I'm not going to do 2 because the square root of 2 is an irrational number, or 3. I'm going to go 4. I'm going to pick perfect squares because that's easier to plot. The square root of 4 is 2. And then I'm not going to go 5, 6. I'm going to go to 9 next because the square root of 9 gives me 3, just to give me some whole numbers to plot. I can't plug in -1 because the square root of -1 is not a real number. I cannot square root a negative because there's nothing that I could square to get a -1. The square root undoes the square, so I can't square root a negative. What did I square to get a negative? It doesn't make sense. So there are no negatives. So my parent function, I'm going to graph 0, 0, over 1, up 1, over 4, up 2, over 9, up 3. I'm off the graph a little. Here's my parent function, and I'm going to graph it in blue just so we have something to work with. Now, this tells me, I took my parent function. This tells me I reflected it. So I know I reflected it over the x-axis. Okay. That negative is my reflection. Times it by 0.5, so I shrunk it, shrink by 1/2, or 0.5. Then I shifted, inside the parentheses is always opposite. Remember, it's x minus h plus k, so it's the opposite here. So the x value actually goes right 2, and then the y value is always straight up, and you go up 2. So remember, opposite, straightforward. This is, since it's a negative, I actually go opposite direction. X value right 2, up 2. So I reflect my original over the x-axis. I shrink it by 1/2. I move it right 2, up 2. Let's just take steps. Let's first reflect it. So if I reflected it, it would look like this. Okay, it would look something like this. This would be the reflection, okay? I'm going to shrink it by 1/2. So all my points, instead of going 1, I'm going to go 1/2. My y points are all going to shrink by 1/2. Instead of going 4, I plug this in and then I multiply it by 1/2 and I make it be negative. So I reflect it over and I shrink it up. Instead of 4, I get out 1. Instead of 9, I'm plugging in 9 and getting out 3. I'm going to get out 1.5. And they're all going to be negative because I flipped them. So let's go ahead and erase. So this is my shrink and reflection. So I'm going to erase this purple and just show the shrink and the reflection. Okay, so in the 0, 0 is still there because when I plug in 0, I get out 0. Then when I get 1, instead of going down 1, I only go down a half. That's my shrink. Instead of going 4, going down 2, I only go down 1. There's my shrink. And instead of going 9, going down 3, I only go down, let's go, ooh, that was supposed to be 1. Sorry. There's 1. And 9, instead of going down 3, I only go down 1.5. So right about here. So here's my shrink. All right. There's my reflection, and I shrunk it up. All right. Now I got to take that, and I'm going to go right 2, up 2. So I'm going to take each of my points and going to the right 2 and up 2. And let's do my final one in red. Right 2, up 2, there's that point. Then I'm going to take my next point and I'm going to go right 2, up 2, right here. It was at a half, it's a half. So I go right 2 and up 1, 2, yes. And then my next point here, I'm going to go right 2, up 2. And then my last point here, it's hard to go right 2 and up 2 because I'm off the graph, but it would be right about here. All right, and so here is what my final graph would look like. Okay, I took the blue, I reflected it and shrunk it in the purple. Then I took the purple and I moved it right 2 and up 2. So I reflected it, I shrunk it, I went right 2, up 2. This is the reflection, this is the shrink, this is the right 2, this is the up 2. All right, guys, if you have any questions, please email me or make an appointment for tutoring or come to my open tutoring hours. And have a good day. Good luck.